In this video, we will talk about Chebyshev collocation methods and pseudospectral methods. And in particular, we will discuss how to take pseudospectral derivatives. In the Lagrange interpolation video, we introduced Chebyshev-Gauss-Lobato nodes, which are given by this expression here. And these are the extrema of a Chebyshev polynomial of degree n, and they include the endpoints on the left and right of our domain, A and B, and this is why we call them Lobato nodes. In the previous video, where we discuss Lagrange interpolation and differentiation using finite difference methods, we discussed how we can calculate the interpolating polynomial going through a number of nodes and evaluate the derivative of that polynomial, and then evaluate the derivative on a particular node. And we managed to write this operation as a matrix operation, where the matrix Dij, which amounts to a Lagrange basis polynomial Pj of x evaluated at a node xi, and we call that matrix D or Dij. So we show that you can simply construct a matrix, differentiation matrix based on these Lagrange basis polynomials, and then dot this matrix onto a vector of function values, and then obtain the function derivatives at those points. If we want to use equidistant nodes or Chebyshev nodes, none of these equations changes, which means that we can use the same methods that we used in the previous video for finite difference methods. We can use the same expressions, the same constructions for pseudospectral methods or for Chebyshev collocation methods. And in particular, any order derivative can be approximated in the same way as before. And the only thing that changes is the set of nodes that we're using. So this formula will stay the same, but it will be evaluated at different nodes, which means that our finite difference derivative matrix and our pseudospectral derivative matrix, they will be slightly different. But the argument that goes into constructing those matrices is a bit different because the grid points are different. But the equations for constructing those matrices are the same. They simply consist of the Lagrange basis polynomials differentiated and evaluated at a set of grid points or nodes. With that in mind, let's go to Mathematica and revisit the Lagrange interpolation with Chebyshev nodes. If you haven't watched the video on Lagrange interpolation, then please go back and watch that first and then come back here. So in that video, we showed that we consider the Runge function and showed that if we interpolate it at the set of nodes given by this formula, the Gauss, Lobato, Chebyshev nodes, then we were able to construct an interpolating polynomial. Let's look at a polynomial of 16th order, and we could avoid the Runge phenomenon, and we demonstrated that the error is distributed more evenly in the whole interval from A to B if we use this set of nodes. So in particular, this exact function in blue and the interpolating polynomial in orange, they begin to really overlap if we increase the number of nodes as shown here, and the error shown here decreases. So if we build a high order Lagrange interpolating polynomial that covers the whole domain, the whole grid from A to B, then we can simply differentiate this polynomial and then evaluate the derivative at each of the nodes shown here in blue. In other words, we can construct a differentiation matrix in the formula using the formula we just showed, based on one single high-order Lagrange interpolating polynomial going through all of these nodes. In the previous video, we showed the command using ndsolve from Mathematica that could be used to construct a finite difference derivative matrix. We can apply the exact same function in this case and simply change the grid that we use as input. So instead of difference order 2 or 4 that we used before, now we can use a difference order that is commensurate to the number of grid points we're using. So in particular, if we're using n grid points, or let's say we're using, well, the number of grid points is going to be the length of the grid x. And then if we want to calculate the derivative, the first order derivative, then the difference order will be the number of grid points minus 1, because when we take a derivative, the order of the polynomial decreases by 1. Similarly, if we want to calculate the second order derivative, then the order of the polynomial decreases by 2, and so we have fewer coefficients available to fit to interpolate the function. So the difference order decreases by 2, and so on. So by specifying the difference order to be this quantity here, the length of the grid, or the number of grid points, minus the order of the derivative, we're using the maximum possible order that we can, based on the number of grid points that are available. Of course, this is only wise to do if your nodes are Chebyshev nodes, because if they are equidistant nodes, you can do this, but you may run into very high errors due to Runge phenomenon. We could accomplish the same thing by using the same command and then saying difference order pseudospectral. And then Mathematica knows that we will be using a pseudospectral method to compute this derivative matrix. And ideally, this command and this command should be equivalent as long as we use Chebyshev nodes. These two commands should give the exact same result because they both use the Lagrange interpolating formula that we introduced earlier. So with that in mind, let's evaluate this expression and then evaluate this function, the Runge function, on the set of grid points, the Chebyshev Gauss-Lobato grid points. And then let's call the function values y, and let's call the function derivatives dy by dx. And this is the exact result for the derivatives that we will compare to. The numerical derivatives can be evaluated simply by calling this function that we introduced here. Let me get this out of the way. So we pass our grid points as an argument to this function, and then this function will construct the finite difference derivative matrix, or actually in this case it's the pseudospectral derivative matrix. The formula again is the same. The only thing that changes is the argument, the input. That means it's a different set of grid points, but the method itself is the same. So this is very convenient because, as we will see later, you can switch between finite difference and pseudospectral methods simply by changing your grid points, and the rest of your code can remain the same. So I highly recommend using this infrastructure for numerical analysis. So here, if we construct this derivative matrix, we get a list of lists. That's an n by n matrix. So let's close this cell down and see what happens when we hit the function values with this derivative matrix. But one comment I want to make is that if we look at this matrix, it's actually a full matrix. There are no zeros. So that's a major difference with respect to compared to find difference methods where we had a lot of zeros. It was a sparse array. For pseudospectral methods, these matrices are full. And we will discuss later what this means about the speed of computations and matrix multiplications and so on. So for now, let's simply dot this matrix onto the function values, and this should give us a pseudospectral approximation to the derivative. And before we discuss the accuracy of the method, let me just add this as a comment here. If we wanted to evaluate the pseudospectral derivative directly, we could do it using the same syntax introduced in the previous video, where we use the dissolve finite difference derivative command, and then we pass the grid points and the function values, and we specify the difference order here for if we want to calculate the first order derivative. We use derivative 1 and then subtract 1 from the length, or we could use pseudospectral here, and this would directly give us the pseudospectral derivatives without going through the step of constructing the matrix. But the reason we want to construct the matrix will become clear later when we discuss the method of lines for solving PDEs or partial differential equations. In that case, it will be much more convenient to construct these matrices and combine them with the time step methods that we need to use. So for now, let's look at the error. We can calculate the error by simply subtracting the exact derivative from the numerical derivative. So let's do it in that order. So this is the error, and to calculate the error, after we subtract the numerical, the exact result from the numerical derivative, we can calculate the absolute value and then the mean, for example, or we can calculate the total, summing the absolute values of all these errors. So that's the average absolute error, and that's the L1 norm. And again, these two do not coincide because they're mean, when we calculate the mean, that divides by the number of grid points. Whereas the total just sums over the errors without dividing by the number of grid points, so it's not normalized. This is why this error is larger. And of course, if we use more grid points, so let's try 64, and the accuracy of interpolation gets better, therefore the accuracy of numerical differentiation should also get better. I don't have to call this function again. I can just, I don't have to define this function again. I can just call it and calculate these derivatives again on the new grid. So now we have more points, and now we see that the errors get a lot smaller. We can also do a list plot to see how these errors are localized. So let's do a list plot of these errors. And what is actually more informative is to do a convergence study and see how the error drops as the number of grid points increases. So let's try and do that. To do that, let's first clear this definition of x. So x equals dot clears the value of x. And then let's define this function x of n, which will construct a different grid when we call it with a different argument n. So n is the number of grid points, and this can construct a grid of arbitrary size. And we'll try and construct grids of different sizes and build polynomials that interpolate the whole grid, differentiate them, and see what the accuracy is. So we will try 25 different resolutions and store the errors inside this grid, this list, which we'll call error list. And let's zero out this list. We can use a constant array command to construct a list full of zeros, and then we will update the errors after we do our numerical differentiation. So to do that, we will use a do loop that goes through different resolutions, and let's try and go from 8 to up to 32. And for each of those, we will evaluate a new grid, x of n, and then calculate the function values at those grids, and then the function derivatives, and then the numerical derivatives constructed by building this differentiation matrix for the first derivative, and then dotting that matrix onto the function values that we computed here. And then we can calculate the mean of the absolute value of the error for each of those values of n. And because n goes from 8 to 32, but we want the first element to be 1 in this list, we calculate n minus 7. So the first element would be 8 minus 7, which is 1. So that will be the first element that will be updated in the first step of this loop, and the next steps will update the rest of the values. So with that in mind, let's execute that loop, and let's copy and paste the error list and see what we have here. And we see that for lower values of n, we have a higher error, and as the number of grid points increases, the error goes down. So let's try and put this in a plot. So we can use list plot to display the error. So here, let's construct a table of the number of grid points and the associated errors for it that corresponds that correspond to each of those n values, and do that for n from 8 to 32, and this is what we get. So as we've discussed before, Chebyshev collocation methods for smooth functions converge exponentially, and indeed what we see here looks like exponential convergence. Of course, there's a difference between even and odd values of n, but on average the drop-off of the error is exponential. That's much faster than finite difference methods, where the error drops off as a power of n. So for a fourth order method, the error drops as a fourth power of the spacing. So in other words, as 1 over n to the fourth. But here it falls off as an exponential to the minus n. So to see that more clearly, we can calculate the log of the error. So let's do the same calculation, but compute the log base 10 of the error here. And let's specify here that this is the log. And indeed, this looks very linear. So we could also do a fit here and show it more concretely. But already this is proof that pseudospectral methods or Chebyshev collocation methods converge exponentially for smooth functions. And just to look at the error one last time, let's go back to our grid and try 128 points. And here, let's construct this exact derivative and the numerical derivative. And we see that the error did not drop. Or actually, these are the numerical derivatives. The error is computed by subtracting those numerical derivatives from the exact derivatives, or vice versa. So we see here that the error is going to be around 10 minus 10 for the mean error, or 10 minus 8 for the L1 norm. And we can try even more points. Let's try 256. Here the interpolating polynomial is very accurate. It's basically accurate to machine precision. And let's calculate the numerical derivatives again. And now we see indeed that the numerical derivative is accurate to about 14 digits of accuracy. So the average error is of order 10 to the minus 14. And of course, this accuracy is well beyond the reach of finite difference methods. So again, for smooth functions, pseudospectral methods are very powerful because of this exponential convergence that we just described. The accuracy falls off faster than any power of n. In other words, it falls off exponentially. So pseudospectral methods are highly recommended for problems where your functions are smooth. And that concludes today's video. Thank you for watching.